Okay, it's just turned midday UK time. So again, welcome to everyone who's joined this webinar on longitudinal tunnel ventilation with jet fans. My name is Fatih Tarada from Mojet Ventilation. And I will just, first of all, start off, if you don't mind, with thanking, apologies. Thanking our sponsors and our partners, TLT Turbo, the Cardenas, and VID Firekill. Just a few quick words before we launch into the webinar proper. We don't have a raise your hand function here, but you're very welcome to type in any questions you may have. There is a box for doing so. I'll try and answer your questions at the end of the webinar. We may run out of time, in which case we'll try and email you some answers after the webinar. And we'll make sure that you have a copy of the presentation either to download at the end of this webinar, or it will be emailed to you. It just depends on how we do for time. Okay, so let's just go through the contents of the presentation. So I want to talk to you about the evolution of jet fan technology, something about the pressure drops along tunnels, which is what we're trying to overcome with jet fans. I'd like to talk to you about jet fan inefficiencies as well. Some of our full-scale tests that we've carried out. Obviously, the main subject of this webinar is the installation factor CFD calculations. And I'll also give you access to our online calculation tool. And then we'll get on to the questions and answers at the end. So obviously, over the last 50 years or so, we've had this evolution of jet fan technology. So around 50 years ago, the conventional jet fan was developed. Essentially, it's a fan in a tube, and the fan is there to impart momentum into the tunnel flow. Jet fans with deflectors came about around 30 years ago, and the idea is to deflect the airflow away from the soffit and away from the corner of a tunnel to enhance the thrust in that tunnel. Slanted silencers came about around 25 years ago, and again, it was the same idea, but obviously it takes more space than a conventional jet fan. And the present, we have the Mojet, which again, the idea is to turn the airflow away from the soffit or the corner. So what I'm trying to show you in this webinar is that actually the Mojet improves your energy efficiency and requires fewer or smaller fans. Therefore, you can save with this technology. Now, if we look at the tunnel ventilation with jet fans, generally, what are we trying to do? We're trying to induce flow from the inlet portal and discharge it to some kind of exit portal. And in doing so, we have to overcome aerodynamic pressure drops into the tunnel, along the tunnel, and of course, out of the tunnel, where we may have, for example, some wind impingement or some other losses at the outlet. So in order to do that, we have to deliver a longitudinal thrust to the tunnel air to overcome all these aerodynamic pressure drops. One of the pressure drops that we've got to overcome is actually nowadays fire suppression, particularly for road tunnels, because what we've actually got to do in tunnels that do have fire suppression is that we've got to accelerate the flow, or the water flow that is, from an initial quiescent state to approximately the same velocity as the tunnel air velocity. And in doing so, we are generating effectively a pressure drop. That pressure drop can be estimated quite simply through the product of the mass flow of the water times the velocity of the air. Now, why am I highlighting this? If you look at the pressure drop for example, a 2 kilometer long 3-lane road tunnel without fire suppression, you can look at all the various components of the pressure drop, and you've got 175 pascals in total. But if you look at the situation with fire suppression, we've kind of nearly doubled the pressure drop along the tunnel, and the majority of the pressure drop is now down to fire suppression drag. So it is something that we have to bear in mind. Now, if we look at the key inefficiencies of standard jet fans, we have aerodynamic, mechanical, and electrical inefficiencies. Typically, these two, the mechanical and electrical, may cause something like 8 to 12% of the inefficiency. But if you look at the aerodynamic ones, these actually cause 30 to 50% of the inefficiency. Okay. If I can just turn off my webcam. Apologies for the webcam getting in the way. I hope that is better. Apologies, 1 second while I just go to the correct part of the slides. Apologies for that. Okay. So if you look at the mechanical and electrical inefficiencies, that will cause about 8 to 12% of the inefficiencies, whereas the balance of the inefficiencies are really down to the aerodynamic and the aerodynamic losses due to the Coanda effect, and that is the friction between the jet and the tunnel surfaces. Okay. Now, one of the things to bear in mind is that fan inefficiencies actually have a direct correlation with acoustic parameters. So basically, if a fan is inefficient, you're likely to have higher sound power levels as well. So the more efficient the fan is, the better your acoustic parameters will be. So if we look at the adverse impact of the Coanda effect, essentially what happens is, okay, the way I've drawn it is this jet is quite close to the soffit and it sticks to the soffit, and you've got this aerodynamic friction against the flow direction. But even if this fan was installed quite a large distance away from the soffit, it would bend towards the soffit via the Coanda effect, and the friction would then lose us a lot of the thrust. So typically about 34 to 40% of the thrust is lost via aerodynamic friction. In extreme cases, we've actually measured it to be over 50%, and I'll come to that in a second in relation to one of the sets of full-scale tests that we undertook. So if we install deflectors, which is another technology available, they reduce the performance of the jet fans, particularly on reversible ones. And of course, unfortunately, they also increase the noise levels. So this is not a technology that we particularly recommend. What happens with the Mojet? The Mojet actually deflects the airflow away from the soffit. So we're reducing the aerodynamic friction between the jet and the soffit. And of course, we're enhancing the tunnel thrust, which is the objective. Another issue where the MoJet helps us with is to reduce the interaction between banks of jet fans. So even if we separate jet fans with the standard rule of 10 tunnel hydraulic diameters, we often find that the jet from an upstream jet fan can be ingested into the downstream jet fan. And that leads to a phenomenon which we call blade unloading. This blade here is unloaded because it's ingesting a high-speed jet. And of course, this jet here has to flow over essentially a metal object. So it's got some form drag that you have to account for. So because of these two reasons, the ingestion of the high-speed jet and this additional form drag, conventional jet fans actually suffer from jet interaction effects. With the MoJet actually reduces the jet interaction significantly because we're bending or we're turning the jet away from the soffit. Therefore, this jet is very unlikely to be ingested into the downstream MoJet. Let's talk a little bit about the full-scale tests that we have undertaken. First of all, at the Mersey Queensway Tunnel. So this was with a 1.25 meter diameter jet fan. And in fact, we used the same fan for the tests. It's only the silencers that were replaced. So in this case, you can see the blue line indicates the MoJet silencers and the red line indicates the conventional silencers that we used. This was a typical horseshoe type tunnel or arched type tunnel. And the clearance between the silencer and the soffit was approximately 350 millimeters. So a reasonable clearance, you would have thought. So the measurements involved taking a 6x6 grid across the cross-section of the tunnel with a 1 minute average per reading at each point. And actually, the MoJet increased the internal thrust by, well, 28.6 or nearly 30%. We calculated the same case using ANSYS Fluent with the K-omega shear stress transport turbulence model. And it showed us very clearly what was going on. Essentially, with the conventional jet fan, the jet was effectively bending upwards slightly and then contacting with the soffit. And that caused a lot of shear to occur and hence a reduction in the thrust. Whereas with the MoJet, the jet was actually turned downwards. You can see very clearly the contours of the jet. So we missed the soffit and we enhanced the thrust in the tunnel. So if you look at the calculated versus measured results, you can see here, this column here is the CFD result. And these are the measurements here in this column here, the second to last column. And actually, we got excellent agreement between CFD and measurements. The difference was only about 1%. So we were very pleased with that. What we then did was we actually extrapolated our results for various tunnel velocities for this particular tunnel. So it appeared that actually over the range of velocities, the MoJet installation factor is very high. It approaches unity and then drops off slightly as you get to a higher velocity of around 6 meters per second. Whereas for the conventional jet fan, the installation factors actually drop quite rapidly. And if you look at the other, the standard correlation, which we call the Kempf correlation for the jet fans, it doesn't really do a good job at all because it's actually predicting a constant installation factor with respect to tunnel velocity. Whereas in fact, we see that it tends to drop with increasing tunnel velocity. Now we move on to another test that we undertook, this time at the Montgomery Tunnel in Brussels. And you can see here, this is the North Portal. This is quite a different tunnel. As you can see, it's a rectangular cut and cover type cross section. In this case, we actually undertook the test with 3 fans towards the southern portal. And in this case also, we only replaced the silencer, in this case only the discharge silencer, because these were unidirectional jet fans. And in this case, we try to arrange for the MoJet to blow towards or away from the corner and towards the tunnel center line. We retain the inlet silencer as being a conventional one. And again, we undertook quite extensive CFD analysis, as you can see. Here's the jet fan in the corner. And also, we kept the same fan, and as I said, just replaced the discharge silencer. So in terms of velocity contours at the discharge portal or the north portal, you could see with the MoJet that we got significantly higher velocities because a lot of it is in red on the right-hand side. With the conventional one, somewhat lower velocities. And if you calculate what these measurements mean, well, the MoJet installation factor was about 0.53, which doesn't sound very much. We're only generating about half the theoretical thrust. But if you compare it with the conventional one, that's far worse. That's only 0.25. What is happening to the streamlines? Well, the streamlines with the MoJet are bending away from the corner and mixing well with the flow, with the tunnel flow. Whereas the ones for the conventional jet fan are actually sticking to the corner, generating a lot of shear and also being ingested into the downstream jet fan. So these two effects combine to give us a very low installation factor. If you look at the ISO surfaces as well, you can see the ISO surface with the MoJet in blue. These are the 10 meter per second ISO surfaces. So in this case, the conventional jet fan has a very long throw, okay? The 10 meter per second persists for a long time, which is not particularly good. Whereas the throw for the MoJet is much, much shorter. It mixes well with the tunnel flow, which is precisely what we're trying to achieve. If you look at the wall shear stress comparisons as well, so the one on the left is the conventional, the one on the right is the MoJet. You can see that the shear stress along the walls and the soffit is reduced significantly with the MoJet compared with the conventional jet fan. So in terms of the measured flow, we got a thrust increase of around 106%. This is based upon the measurements, based upon this grid of keel probes. So we had, in this case, we had 5 times 5 grid of keel probes. And here's the actual air velocities. As I said, the MoJet just under 5 meters per second, whereas the conventional jet fans only gave us around 3.65. So that confirms that the increase, the MoJet to conventional jet fan thrust ratio was around 2. And in fact, we measured a very slightly lower power consumption for the MoJet compared to the conventional jet fan. Now we move on to the 3D calculations of these jet fan installation factors. So what we've done here is a comprehensive set of calculations based upon various geometries. So in terms of the rectangular tunnels that we investigated, these were 2-lane road tunnels with a hard shoulder, with an overall width of just under 10 meters wide and 6 meters high. And we investigated 2 jet fan diameters, 1.25 meters in diameter and 710 millimeters. That's the kind of the range of most tunnel jet fans used in the market today. And there they are here, the 1.25 and the conventional. In terms of the fan positions, and you will see some of the analysis in a minute, We distinguish between the clearance. There's an overall clearance here between the corner or the soffit and the internal part of the fan, and also the clearance to the outside of the silencer. And that's the same for the flat soffit and the corner. We've also undertaken a lot of analysis for the arch tunnel profile, although I won't be presenting the results for that yet because we are still completing that set of analysis. So where you see clearance in my analysis, it really means the overall clearance here to the inside of the jet fan. If you want to get to that from the clearance to the silencer, you simply have to add the thickness of the silencer material. So how did we actually analyze the internal thrust based upon our CFD analysis? Essentially what we did was we had to add the pressure force difference across the tunnel, plus the momentum force difference, plus the wall shear force difference. So by adding these three elements together, we could estimate the real or internal thrust generated by a jet fan into the tunnel air. So many of you will know and love this equation for the internal thrust of a jet fan, and included within it is the installation factor, this eta I. This installation factor we have broken down into three parts. The first part is a factor for the velocity, the clearance, and the fan diameter. Then we have another part for the longitudinal fan spacing, and then a third factor to account for the friction coefficient. What we've done is we've derived these three factors from our CFD calculations. And in order to do so, we have varied the tunnel velocity, the fan spacing, the friction factor, fan diameter, and the clearance of the fan from the nearest tunnel surface. So let's have a look at the installation factors we've calculated versus fan spacing. So this is for a jet fan diameter of 710 millimeters and for a fairly modest friction factor of 0.021 and for a tunnel velocity of 3 meters per second. What you're seeing here is as we open up the spacing between the fans, certainly for conventional jet fans, we are tending asymptotically towards a value for the installation factor, which is effectively the installation factor for a single jet fan. As you bring the fans closer together, the installation factor actually reduces markedly, certainly for conventional jet fans. Whereas for the MoJet, you really have to go very, very close together to influence the installation factor. Installation factor doesn't change very much unless you're very close together. And essentially the same applies here. This is essentially for a different clearance. This is a larger clearance. So you can see that the asymptotic value, which is the dotted line for the MoJet, is now higher. It's tending towards approximately 0.9, whereas for the conventional jet fan, we're asymptoping towards more like 0.75, something like that. And we've repeated this actually for various clearances. Here's another clearance. One thing to note that in every single case we've investigated, the MoJet is at least as good as, if not significantly better than, the conventional jet fan. And here is another case in hand, for example. So this is actually for a soffit, a flat soffit. And as you can see, for a flat soffit, we're asymptoping towards a unity installation factor with the MoJet very quickly, I would say, with the spacing, whereas with the conventional jet fan, you really have to space your fans quite far apart, and then you're not asymptoting anywhere near a unity installation factor. So if we look at what happens with the tunnel velocity, as you increase the tunnel velocity, what tends to happen is that the installation factor tends to initially reduce. We think this is because the friction patch between the jet and the soffit tends to be extended, and that friction patch, because it's bigger, is causing you more of a pressure drop. After that, it can tend to increase, and we think that's because of the increased mixing between the jet and the tunnel air. So therefore, in effect, your friction patch length reduces again. But again, you can see very clearly that the Mojet provides superior installation factors compared to the conventional jet fan. Here's an example with a corner. You may notice that we've actually non-dimensionalized the tunnel velocity. In fact, when you eventually see the correlations, you'll see that they all use non-dimensional parameters. This is very important for us. Now, here's a case when the installation factors for the two jet fans is almost the same. So at very low tunnel air velocities, you can have a situation where the installation factors for Mojets and conventional jet fans are similar, but anything beyond a very, very low tunnel velocity, the Mojet is superior. Again here, this is for soffit with the smaller jet fans, the 710mm jet fans. And again, in this case, you can see that we've got this reduction, in this case, a monotonic reduction in the installation factors. With the smaller jet fans, we don't seem to get the pickup in the installation factors with the higher tunnel velocities. And this is also confirmed here. In terms of the friction factor, well, if we increase the Darcy friction factor in a corner, then we do tend to get a reduction in the installation factors, more so for the conventional jet fans compared to the Mojet. There is also a drop in the Mojet installation factor, but not as much as the conventional jet fan. For a soffit, we don't seem to get much of a change with the Mojet, but there is a bit of a change with the conventional jet fan. It does drop as we increase the friction factor. Just a few more images to confirm what I've been telling you. So here's the wall shear stress for a conventional jet fan underneath the soffit. As you can see, you've got quite a big friction patch, as we say, where the jet is sticking to the soffit and causing us pressure loss. Here's the equivalent friction patch, as we say, for a Mojet. It's much smaller, and hence we're losing less shear that way. If you look at apologies, can you now hear me? Okay, right. I hope you can hear me now. Yes, you can hear me. That's excellent. Thank you. Apologies for that small technical hitch. So, and I'll just go to the correct slide as well. Okay, right. So we've got the friction factors and we've got this wall shear stress. Okay, so I think we got to this bit here. Okay, 1 second while I just enhance this. Very good. So what we've got here is as we increase the tunnel air velocity, we tend to get this ingestion of the jet into the downstream jet fans. And this is the issue that I mentioned to you earlier. With the MoJet, what tends to happen is that, and this is, you're looking now at the MoJet soffit case, you actually get quite a good profile of velocity upstream of your downstream jet fan. So therefore, you get much less ingestion and less blade unloading. This is just an example of the kind of streamlines that we can expect. So this is with the MoJet here. Essentially what we're doing is we are deflecting the airflow down away from the soffit. And this is the situation with a conventional jet fan. And unfortunately, the airflow is actually bending upwards towards the soffit. Okay. Right. This is the bit that perhaps a lot of you are really looking forward to. So this is the link to our installation factor calculations. I will share this with you shortly. I will try and upload the PowerPoint presentation for you as a PDF file. It is a test version. We are currently developing a permanent version, which should also include the arched tunnel profiles. So obviously we welcome your comments and questions. Please send them to this email address. When you come to run the installation factor calculations, you will see a panel like this. So on the left-hand side, you will see this question related to the position of the jet fan, whether it's a flat soffit or a corner, or indeed later on it'll be an arch soffit as well. You have to enter your tunnel velocity, your fan clearance, and this is to the silencer, and then the silencer thickness. Internally, these numbers are simply added together to generate the overall clearance. The fan spacing, the fan diameter, the jet velocity, the hydraulic diameter of the tunnel, and the tunnel friction factor. And then what you get here is the MoJet installation factor, the conventional jet fan installation factor, and the percentage improvement of the MoJet above the conventional. We are writing a technical paper for the Graz Tunnel Ventilation Conference. And for those of you who are very interested in the mathematics, all the formulae used in our correlations will be explained there. So I conclude now by saying that CFD simulations can provide an accurate estimation of the jet fan thrust compared to measurements. We've proven that several times. The jet fan thrust can be significantly reduced for conventional jet fans through the Coanda effect and also through blade unloading, which is the jet ingestion problem. MoJets give you an opportunity to reduce your jet fan numbers and your power consumption. And of course, in order to help you do that, you've got an online tool to help you estimate those values. So thank you very much. I will now take some questions. Let me just switch this on, and now I will look at your questions. 1 second, please. Okay. Right. I think Ferdous has asked me what I mean by MoJet. Okay, that's a good question. Okay, so MoJet is essentially a jet fan with a shaped silencer. I think that's probably the best way of explaining it. Okay, right. So let me do one thing now and actually attempt to put in a handout for you. 1 second, please. Okay, so for those of you lucky enough to see this, there should now be a handout for you under handouts, which you're very welcome to download. Okay. And of course, MoJet is a product that is manufactured by our partners, TLT and De Cardenas. And as I said to you, you're very welcome to visit their websites and to contact them directly with any queries. Right, I don't see any more questions at the moment, in which case I'd like to thank you very much for attending this webinar, and hope that you engage with us, contact us directly, and by all means join our next webinar. Thank you very much. Bye-bye.